So I got a good question about the comfort variables in the psychrometric chart um, that we didn't discuss in class, and so I thought to answer that question I would just do a longer video on the psychrometric chart. It's completely optional. I've said that we in class we're covering fundamentals more than we have in the past in this course, but we're just scratching the surface, and so for anyone who's interested, there's always going to be a lot more to learn. I'm still learning about this stuff, so maybe sometimes I'll just do another little video. Again, optional. So the first point to make, we're in the psychrometric chart. I don't need to have any climate data in here to understand or to learn something here or to use it to, I guess, test my knowledge is one way to put it. Um, uh, these things, if you're just reading a book or listening to a lecture, you're not going to be able to pick them up the first time. It takes a while. You have to think about it, internalize it, and I think this chart is a good way of doing that. So remember that we have this target that you can move around. So let's just go to a 80, 80 degrees, 50% relative humidity, and then we have this summary up here. So we're at 80 degrees, 50% relative humidity. Absolute humidity is what's in the y-axis because we're saying this is the actual amount of water. So if I've got 0.0111. That's true. That's the same as this. So I'm just checking my understanding. 50% should be what we're at. Yeah, 50%. Okay. Vapor pressure and air volume, I wouldn't worry about those. Those are more HVAC centered. Let's just skip them for this semester. Enthalpy, though, is good. Because that's a weird word. It's kind of hard to maybe wrap your head around it. You can look up the definition. But for us, what it means is just the total heat. And so we could surmise that if we are at 80 degrees Fahrenheit and we go, see, our enthalpy is 24, but 23.5 right now, and I head upward, I'm going to increase my enthalpy because I'm increasing the amount of water in the air, which is related to latent heat. And we've talked about the difference between sensible and latent heat. If I move to the right, it should also go up. I'm at 31 because this is going to increase the sensible heat, and it is. And so if I head in this direction, it's going to go up even faster because I'm increasing both of them. So that makes sense. Dew point is another really something that I think that can be confusing. So let's play with it for a second. If I'm at 80 degrees Fahrenheit, 40% relative humidity, what is my dew point? It says here that it's 54 degrees. Why is that true? Well, if I'm just looking at the chart, I can go, well, this line, if I go straight over, I get to about 54 degrees. Well, it says 54.13. If I go up a little bit to 80, yes, because I'm not exactly. So yeah, I'm about here. So that would be right. So that line is what's creating my dew point. Why is that true? Well, if I'm at 80 degrees, 50% relative humidity, and I get to 100% relative humidity by just moving directly to the right, I'm going to hit my dew point right here because that's where I have 100% relative humidity, and I'm going to have condensation, or dew is another term for it, right? So that's around 55 degrees. So it makes sense. This is just a really accurate number. Wet bulb is the final thing we might want to consider here. If I turn on the wet bulb indicators, just these diagonal lines, but remember what they are is it's a number that we can use to correlate dry bulb and relative humidity in one number. And so in other words, if I'm at 80 degrees Fahrenheit, 50% relative humidity, my wet bulb is going to be following this line around 64 degrees. That's basically what it says here. What does that mean to us? It just say it's a way of the closer that our the closer that our wet bulb is to our dry bulb, then the more. So if I go up, right, if I go straight up to 100% relative humidity, then my wet bulb and my dry bulb are the same. Dry bulb, wet bulb. So the closer my wet bulb is to my dry bulb, the wetter the air is. And so if I'm looking at something like a climate file, so I have one here. We talked about this in class. So this is the wet bulb, this is the dry bulb. Let's open this up. Wet bulb, light blue, dry bulb, dark blue. Just generally, the closer these are to each other, the wetter the environment. So if we're looking at climate file, we can get a feel for how wet it is by just looking at those two variables. All right, so that's how we play around with the chart without anything in it. And then the thing is that we are only plotting temperature and relative humidity, but there are other variables that determine comfort, right? We said it's dry bulb temperature, so sensible heat, relative humidity, airspeed, mean radiant temperature. We also have clothing, because the more clothing you have, or more or less, will change the comfort zone that you can, or how comfortable you'll be in whatever temperature and relative humidity it is. Um, so there are ways then that we can bring those metrics into our psychrometric chart also, and there are different standards that allow us to do that. So let's just then first bring in some climate data. So right now I'm in Miami. I think I'll change it to New York, um, just because we know that better. So I'll just do Central Park. And what we're generally going to be doing in class is using this overlay, because these are all the broad passive strategies that we're going to be talking about later in the semester. And so the game we're playing is, given our climate, what strategies will be the most sensible to use, or not? Yeah, the most. I shouldn't use the word sensible maybe, because that's sensible heat, but the most that will make the most sense. Um, so this is a great overlay to use, but let's check out some of these others. So what's the ASHRAE 55217? So we have a different comfort zone that's defined, but the main thing to understand about this this standard is that we are taking into consideration other, or we can there's a range of air velocity, clothing, metabolic rate, and mean radiant temperature that the standard allows to see whether or not you're in the comfort zone. So we can right now these are automatically set at what the standard requires, and so then you'll see that right now we're not compliant because our markers outside of this comfort zone. I bring it in and we're compliant. But this was the question that came up that I thought was good, and that led me to make this video, is that we have these other variables now, like SET, PMV, PPD. So what are those? First of all, it was like late in the class, and I was just like, oh, yeah, let me look at that later. I don't really want to try to figure it out or remember it right now or talk about it. Just like anybody else, I've got a bunch of stuff in my head, and I don't always remember things. I often don't know things, which is, that's just the way it works, right? We're always learning. So to remind myself, what I did is I just went to AI, and I want to show this just because I think I've talked to the classes I'm teaching this semester, and it seems like not that many. Well, I don't know, maybe you are, maybe you aren't, but I didn't get a lot of hands raised when I've asked about it. So let me just dive in really quickly. And I'm using Edge all the time now, not Chrome or Firefox. And one reason why is because we have it has a good AI chatbot, and we have a pretty robust free license with our whatever license we have with Microsoft 365 through NYIT. So if I just go to a new browser window, the way I have mine set up, I can just click on the chatbot here, and I come to this window. So I did that, and I just put in. I asked AI to compare ASHRAE 55217 with EN 15251, and that's another standard that's available here. So yeah, we're getting more into the weeds now. Like, I didn't want to go that deep into class, but if we're looking at these, so these are more about they're more detailed in terms of the other climate or comfort variables. And if we look through so first of all, EN is a European standard. It has different goals. ASHRAE 2021 is basically focusing on comfort, or passive comfort. And so you could read through this, and my point is simply that it's easy to use AI to make these kind of comparisons. You can ask it to make a chart. Just realize when you do use this that this is an active participation. This is a tool for you. It's like your assistant. You have to be, it's very often wrong, or it very often takes you down what we'd like to call a rabbit hole that is not productive. So remember, it's your assistant, it's not your teacher. Okay, so but the point is, I'm looking through this, and we're, as I would assume, we're talking about PMV, PPD, and SET throughout, but it doesn't really define them. So then I can just easily, in the same thread, I said, in the context of human comfort, what is PMV, PPD, and SET? And so for example, a lot of times these are confusing. PPD is also a term for things like safety glasses, personal protective devices. And oh, 1 second. Huh. Sorry, I got interrupted there. PPD is personal protective device, also called PPE. So anyway, my point is that these, you don't have so many letters, and so these things overlap. So it's always good just to check yourself anyway. So let's just go through these. So P and V is predicted mean vote, and what that's about is we've mentioned this in class. Like, we don't really have a comfort zone because this is something that we've contrived, and it's based on an average, and so everybody's different, and not everyone will be in the same comfort zone. So the predicted mean vote tells you, well, wherever you are, whatever conditions you're talking about, how many people will find it comfortable, or slightly warm or hot, and the same thing, slightly cool or cold. And so it gives you a range and an understanding of that range in a simple metric. Then PPD is predicted percentage of dissatisfied. So that is basically, and by the way, if you look at that, yeah, right, I think it's right here. Neutral is 5%, basically saying we're never going to please everybody. So that it's related to PMV, but just kind of a different take on it. So it's like predicted mean vote is how many people are comfortable, and are they, slightly warm, or hot in this condition, or how many are those different variables. And then predicted, the PPD is just what percentage is going to be dissatisfied with the conditions you're talking about. And then finally we have SCT, which is standard effective temperature. That I'm gonna, well, let's go back over PMV and PPD really quickly, and then I want to do something different to do standard effective temperature. Okay, so if I am right here in the middle of the comfort zone, I can see that my PMV is 0 and my PPD is 5%, which means neutral. If I start moving out of the comfort zone, I'm getting higher numbers for these, and then eventually I get out of being compliant. I'm out of the defined comfort zone. Let me come back in. So that's the way that works. There are different. You can see down here we have the PMV is mapped onto the comfort zone. We're saying if we, and this is the standard. If we go below 0.5 PM minus 0.5 PMV or plus 0.55 PMV, we're going outside of the comfort zone. So that's in the standard. So that's basically what those two terms mean. And maybe before I go to SET, let's just play around with this here in the chart. So the other thing we can do with this Andrew Marsh psychrometric chart is change the comfort variables. So so here I am, I'm in the comfort zone at my set set point here, and what happens if I increase the air velocity? Well, it's going to reduce the it's going to truncate the comfort zone. Let me go to. Yes, that's interesting to me. I would think there's a certain. So so basically what it's saying here is that at zero air velocity we have the widest comfort zone, and then as we increase it, the comfort zone gets smaller, but more toward the cold than to the warm, because we can feel comfort from wind when it's hot outside. If I change the clothing level, I actually move the entire comfort zone, because as I'm getting as I add clothing, it can be colder. As I remove clothing, it can be warmer. The metabolic rate has to do with how fast we're moving. One is basically seated. So if I start running around and I'm very active outside, I'm building a house or whatever, my comfort zone moves downward, and I can be comfortable when it's colder. That's why it's more comfortable to work in slight winter than in intense heat of the summer. Um, and then I can also move my mean radiant temperature, but we'll talk about that in a second when we go to SET. So the point is that we can move our comfort zone playing using this standard. There's other standards we can use to do the same thing, using these comfort variables that we've talked about. So that's a way that you could play around with the chart and try to understand your climate. But also you could decide. Let's say let me go back to this standard. Oops, wrong one. If I know that this is maybe it's on a porch that I have, or a plaza out in front of a building. I've looked into it, and I have a certain temperature that's out of the comfort zone, the typical comfort zone. I could play around with, what's the clo rating that I would need, because you could look up these clo ratings, what they mean in terms of actual clothing, and see if I think it's realistic. I could think about mean radiant temperature, like if I change the surfaces in the area, or in other words, make it more reflective, less reflective, etc., have more emissivity. I can adjust the comfort zone and maybe bring that specific temperature into temperature and relative humidity into my comfort zone for the project. Okay, so the final thing we were going to talk about in terms of these variables is SET. And if we see the definition here, it's basically saying, let's say we have a temperature somewhere. I'm going to turn everything off to talk about this. Sorry. Okay. It's basically saying if I'm somewhere, I have a set temperature and relative humidity. What would be in an ideal situation, in other words, where I had about 50% relative humidity, still air, and clothing insulation of 0.6 clo, what would the person in that environment, what would be the same amount of heat loss that they would experience in that environment? And what that does is allows us to adjust, sort of to make a variety. It's kind of like wet bulb temperature. It allows us to make a variety of environments. We can compare them to each other. But let's just do it as an example. Let's say if I'm at 80 degrees. Let me go to something that's kind of easy to. 80 degrees, 70% relative humidity. Right now it's saying my SC. Oh, I got to go to the right. I got to go to a comfort overlay. I'll come to the ASHRAE 55217. Right now I'm at 80 degrees, 70 Fahrenheit, 70 degrees, 70% relative humidity. My SET would be 77 degrees. So why is that? The best way to understand it is let's bring the air velocity down to nothing. Let's bring the clothing level to 0.6, because that's what it says. Let's make our mean radiant temperature the same as our dry bulb temperature. So I'm going to bring it up to 80. It's hard to get it exact. And finally, the metabolic rate, we'll just play around with until we get. So right now we're at SET 86.5, so I probably need a lower metabolic rate. Yeah. So right here, at a metabolic rate around 1, clothing level of 0.6. So probably if I go to 1, it'll even be better. Now that takes us a little bit high. I have a SET that's the same as my dry bulb. And then if I start changing these variables, I move my SET I create a situation where I have a very different SET than my dry bulb temperature, and then you could analyze why. Now I think you can see why I didn't talk about this in class, because I don't even want to get into more detail about it right now. I think you can, what I'm saying is look at these if you're interested and play around with the chart here and see if you can internalize what they mean. And if not, then the next time this comes up, you'll have another shot at it. Let's look at a couple more of these. So the difference between 55 to 17, one of the differences, and that this European standard is the European standard has more gradations for the PMV. The outdoor heat index we talked about a little bit. Remember that if where this would be more relevant would be if I had a really hot climate like Dubai. So in Dubai, I've got, let's just compare it to New York. I think I have another chart open somewhere. Let's do two. Is that the Dubai one? This is New York. So New York, Dubai. Let me get with the New York one. Let me turn on. The same, this outdoor work. Yeah, so it's clear just looking at this that in New York we don't really need to worry about danger and extreme danger. There's some times we have to be in extreme caution for workers outside, but I'm sure for older people we'd have to adjust it. But one thing to notice here is right now I have a very low solar exposure. If I increase this, it's going to bring this range down. And so if I were I'm working in Dubai at this site, and I see already that I've got a fair amount of danger and extreme danger outdoor conditions. And why is this true? It's because when we get really hot and higher relative humidities, then we can't sweat to cool ourselves down. And if we can't cool ourselves down, we'll overheat and we can die. But the point here is that if I increase the exposure level, so now I have no shade at all. I have a lot more of these hours that are dangerous. So this is an argument for shading, which is kind of obvious in this location, but we can actually quantify. So like if I'm changing the shading generally to where have about half the amount of sun hitting a site, then I can quantify how much I've basically made it safer for people. All right, so I think that's all I wanted to cover. The main message here is if you're, as you move forward in your architectural career, I would just not forget about these charts, and you'll only understand them if you use them. If you're just going to be in New York, remember that it's helpful to. I'm going to change to Miami, because that's something we know about. International Airport. So if I'm going to change back to, let's see, I'll do this one, and here we are for that. So now we're in Abu Dhabi. Let me change this one back to New York. It wasn't the most efficient way of doing this, but okay. So now I have these two charts. I'm going to turn off this. Actually, I'll turn that on in both. So now I have this date range thing. It's helpful, even if I'm not going to be designing in Miami, to use this climate data to make a point about my design. So if I'm saying, I'm making, oops, what did I just do? If I'm making a point about some kind of heating strategy that I've got, or that I'm making a point about passive solar heating. If I have a comparative, if I have a comparative file of climate like Miami that somebody can understand, and I can talk about, well, if we were in Miami, we could do, we wouldn't need to do this, and the thing you just showed me that you like is in Miami, so let me show you why that really is not the best for New York. So it's good to you can use this data and these graphics to compare things to make a point. Also remember that you can choose whatever part of the year that you want to be displaying. So it's a pretty powerful graphic interface here that can help you generate graphics that are useful. All right, I think that's plenty for this beginning course on psychrometric chart. I will see you all in class.